Here is the combined summary. The research explores the entropy of rectifiable and stratified measures in the context of geometric measure theory, focusing on the asymptotic equipartition property and its implications. This property ensures the concentration of measures on strata of a few typical dimensions, leading to the derivation of the entropy chain rule for stratified measures. This chain rule generalizes discrete continuous mixtures and may have a singular continuous part, with the conditional term being an average of the entropies of the rectifiable measures involved. In this framework, the Hausdorff dimension and measure are essential in understanding the volume of non-smooth sets. The research provides a detailed analysis of these concepts, connecting them to the entropy of measures and their properties. The paper also delves into the concept of rectifiable and stratified measures, defining the Hausdorff dimension of a set A as the unique value of M for which the Hausdorff measure M A transitions from infinity to zero. The area and CO area formulas are presented, which are fundamental in computing integrals over rectifiable sets. The area formula states that for a Lipschitz function f Rk right pointing arrow road and a Lebesgue measurable subset E of Rk, the function y right pointing arrow sigma x element of E intersection f caret 1 y u x on road is Higg measurable. The CO area formula allows for the computation of integrals over countably M rectifiable sets as iterated integrals. The concept of countably M rectifiable sets is also discussed, defined as countable unions of M rectifiable sets with sigma finite measures. These sets are crucial in the study of geometric measure theory, and the paper highlights that any subset of an M-dimensional C1 submanifold, differing from it by an H-null set, is countably M rectifiable. The paper explores the concept of rectifiable and stratified measures, focusing on their entropy properties. It begins by presenting a CO area formula for a Lipschitz function f Rk right pointing arrow road, where E is a countably M rectifiable subset of Rk with M is greater than or equal to D. This formula states that the set E intersection f caret 1 T is countably HMD, MD rectifiable and HMD measurable, and the function T caret M ASQRT D right pointing arrow integral E intersection f caret 1 T G Y DHMD Y is LD measurable on road. The CO area formula is then applied to compute the entropy of a probability measure ρ, which is absolutely continuous with respect to the restricted measure E. A key result from Koliander et al. 2016 is summarized, stating that if A is a bounded Borel subset of Rk, f is an injective Lipschitz function on A, and ρ is a probability measure such that ρ much less than Lk, A with density R, then f ρ much less than Hk, f A with density R JKF caret 1, which is well defined, Hk f A almost surely. This leads to the formula for the entropy of rectifiable measures as HHK f A f ρ equals HLK ρ plus integral East ρ lane JKF. The paper also introduces a chain rule for the entropy of rectifiable measures as a consequence of a general theorem for disintegrations. Given a countably M rectifiable subset E of Rk, a Borel function f Rk right pointing arrow road with D is less than or equal to M, and a probability measure ρ such that ρ much less than E, it is shown that f ρ much less than LD, and the entropy can be expressed as HHM E ρ equals HLD f ρ plus integral RKHF caret 1 HMD E intersection f caret 1 T ρ T df ρ. This chain rule facilitates the computation of the entropy of rectifiable measures in terms of the usual differential entropy and the entropy of lower dimensional measures. Furthermore, the paper discusses the concept of stratified measures, which are a sum of rectifiable measures with different dimensions. A fundamental example is a discrete continuous mixture, where each component has its own dimension. The product measure of a stratified measure is also stratified and can be grouped by dimension to be put in the standard form of definition 3. The main result of the paper, Theorem 1, provides a refined version of the asymptotic equipartition property, AEP, for stratified measures, giving an interpretation for the conditional term in the chain rule, 14. This theorem states that for any epsilon greater than 0, there exists an n0 such that for any n is greater than or equal to n0, the restriction of ρ to t, n, delta rho, n, satisfies dTv, rho circled times n, rho, n, less than epsilon. Moreover, rho, n, equals a sum of m rectifiable measures for m element of ne, d, n caret 1/2 plus xi, ne, d, plus n caret 1/2 plus xi. The conditional entropy h, x, y quantifies the volume growth of most doubly typical fibers in the sense that for any y in A, n, delta, 1 has north caret 1 lane him, y, t, n, delta y, is less than or equal to h, x, y, plus delta, n. The paper delves into the entropy of rectifiable and stratified measures, providing a geometric interpretation to the possibly non-integer dimension E, d. This is achieved by considering sets A, n, and B, n, with specific properties, which are used to bound the entropy of the measure m, y, from above and below. The main result shows that under suitable hypotheses, the information dimension of the measure ρ equals the limit of the logarithmic growth rate of the cardinality of B, n, as n tends to infinity. The paper draws upon various works in the field, including the theory of rectifiable sets and tangent measures, geometric measure theory, and the concept of information dimension. It employs mathematical tools such as Federer's geometric measure theory and Ambrosio, Fusco, and Pallara's functions of bounded variation and free discontinuity problems. Moreover, the paper explores the connection between entropy and disintegrations, a concept introduced by Vigneaux in a 2021 publication. This connection is crucial for understanding the relationship between the entropy of a measure and its disintegrations, leading to a more comprehensive understanding of the geometric properties of the measure. Furthermore, the paper touches upon the concept of typicality for stratified measures, an idea explored in another work by Vigneaux in 2022. This concept is essential for understanding the behavior of measures under different stratifications, providing insights into the structure and properties of the measure. In conclusion, the paper presents a novel approach to understanding the entropy of rectifiable and stratified measures, leveraging geometric measure theory, information theory, and recent advancements in the field. It provides a detailed analysis of the relationship between entropy, disintegrations, and typicality, shedding light on the intricate properties of these measures.